现在扣分扣有点多了，那我最近这2个字我已经想起来这个了，然后我就去做写的太少了，2个字。
Yeah, but he didn't realize that there would be class. Yeah, I'm just All right, let's continue. Okay, so before we move on, so quick announcements. So homework 4 is due on Monday. So I plan to have a few. Hopefully, all of you have tried most of the problems, but I plan to have a few hints out for them today or tomorrow. So watch out on Canvas. Okay, so today/tomorrow. This is just because I mean maybe some of you are not that comfortable with reductions and stuff, so I just thought I would do a bit more hints. Okay. The other thing is project meetings. So you should again look for Canvas announcements. But basically, I want to meet every team. Hopefully, either this Thursday, Friday, or early next week. And the goal is we should try to figure out what is expected. What you can try to do for that particular project. Okay? So luckily the spread of projects was very nice. So people I think chose to work on different things. So in that sense it's good. So for every topic I'll have a scheduled slot. Okay? So if you're in that topic, then you can just show up at that time. If it really doesn't work for you, then we'll try some other stuff. So yeah, so again look for the Canvas announcement. Okay, so any questions on this? Yeah. Do you have okay. Okay, so last class we started looking at what we call concentration bounds. And these are essentially the question we ask is you have a random variable. It could be anything, it could be the running time of an algorithm, it could be some quantity that you estimate. Okay, so it could be some estimated quantity. Or running time, something like this. Any random variable. Okay, and we want to know how distributed it is around its expectation. So you could have a distribution where you have a peak like this and you have a peak like this, and the expected value is here, but the expected value doesn't mean much in this setting. Okay. So we are looking for distributions where you have stuff like this, right? So we are looking for like an expected value and then a tail that drops off very fast. And this is what we hope happens with our running times and things like this. Okay, so if you're trying to estimate a certain quantity, then it's really bad if it's in the first situation, right? Because your expected value will be this, but it's never really there, right? So you would want it to be more significant. Okay, so that's why we like to see things of this kind. And we started looking at how you prove things like this, how you prove that a random variable is concentrated around its expectation. And we said that the first thing was Markov's inequality. This is very simple inequality. All it states is that if you have a random variable x that's always non-negative, then probability that x is more than some t times the expected value is less than or equal to 1 by t. And so this at least, it's not very strong, but gives a first cut approximation, like we said. Okay, so we said that, yeah, so we saw a few examples of this. Okay. And then we said that there are more sophisticated ways of essentially proving concentration bonds, and one of the things was variance. Okay, so this is what we looked at last time. So you want to measure how close a random variable is to its expected value. So one way to do it is, one way to measure this is what is called the variance, and the definition of the variance, if you have any random variable x, the variance of x is defined as the expected value of x minus mu whole squared, where mu equals expected value of x. So mu is the mean, which is the expectation, okay? And you look at the expected value of this x minus mu whole squared. And this is, in some sense, this is how much you expect the variable to naturally deviate. Okay, so in your homeworks you'll see that with at least probability of about a third or something, you will deviate at least by this much. Okay, so the variance, I mean, what I mean is, yeah, so the square root of the variance will tell you how much you deviate. So with probability at least a third, you will at least deviate by roughly this much. Okay, so that's why it's called the variance. But the hope is that you don't deviate by much more than this. So that's the goal. This tells you how much. This is an estimate. So let me write down the standard deviation, because that's really how much you deviate. Standard deviation of x equals square root of the variance. Okay, and that's like, so here the variance has a squared here. So you can think of it as the distance between x minus mu whole squared. Right? So the variance measures the actual distance. Okay, so it's not the square of this. So that's this. Okay, and I think last time there was a question in class about why are we looking at the square and then taking the square root of the expectation? Why don't we just compute expected value of absolute value of x minus mu? So it turns out this is messy to compute, because absolute value is something that's messy typically to have. Like a square is a nice function, right? So that's why we go through that. So that's the definition of variance. Okay. And last time we saw one interesting thing. We said that typically when you are estimating a certain quantity, we get multiple independent estimates and we take their average. Okay. And last time we saw why that's a good thing to do. And what we said is, if you have random variables x1, x2 up to xk that are all independent, and also suppose that E of xi equals mu, then variance of the average, okay, x1 plus x2 up to plus xk divided by k, is basically 1 by k squared times the sum over I variance of xi. Okay, so we did this calculation last time, so we expanded out the terms and everything. And the message here is, if xi are all the same, then this is like, and suppose each of them has variance which was, we called it b squared or something, or we called it sigma squared, right? So if each one has variance sigma squared, then this is like, then the variance of this average is sigma squared by k. So the variance drops by a factor of k if you take average over k independent copies of your n. So this is why we always, like, whenever you see any scientific paper, you run experiments multiple times, take the average and draw error bars, right? So this is the reason we do it, because you get a better estimate if you take the average of multiple independent runs. Okay. So that's, yeah, this is kind of the justification for it. Okay. And we used this, so to see an example of this, we said that you can estimate the average of a bunch of numbers, bunch of integers in a certain range by just taking a few samples. We saw how many samples you need and so on. Okay. So, and next, I think I skipped one thing from last time, yeah, which is Chebyshev's inequality. And this is basically, it's an inequality that says that a random variable is not too far from its from the standard deviation. Okay, so what it says is the probability that x is bigger than, or rather x minus mu is bigger than some t times the variance, t times the standard deviation. Sigma squared is the variance, square root of that is the standard deviation, is less than 1 by t squared. And I said last time this is actually a trivial consequence of Markov. It's like applying Markov's inequality to x minus mu whole squared. And yeah, that's why you get the t squared. So yeah, and the definition, the expectation of x minus mu whole square is equal to sigma square. Okay, so that's why you get this. That's why this thing is true. So this is, if you don't see it immediately, never mind. It's a natural consequence of Markov. Okay, so you will actually, in your homework you will see very simple examples of this. So that should drive home the point. Okay, so if you don't see it now, it's totally fine. Alright, so this says, but the message here is, the probability that the variable minus its expectation is more than some t standard deviations is less than 1 over t squared. So if I think of t as 10, then it's saying that with pretty good probability, with probability 99 over 100, I am within 10 standard deviations of my mean. This is a pretty nice result, right? So, I mean, it's a useful fact. And this is true whenever you have some bounded variance. Okay, so as long as the standard deviation is finite, you have some bound line. Okay, so we'll see concrete examples of this. Then we said last time that okay, this is nice, but there is something even nicer, and that is what we call the Chernoff Born. Okay, so this is a stronger concentration inequality, and this is one of the strongest ones we know. Okay, so this actually the version I wrote down is called Bernstein's inequality, and at least wherever I've used Chainoff bonds, and I've used them a lot, this turns out to be much more useful than the original Chainoff bond. It's a very special case of things. Okay, but this is much more useful. What it says is that if you have a bunch of independent mean zero random variables, so why is that not so why is that okay an assumption to make? This xi's are mean zero and
you could always center your
yeah, so whatever, if your random variable did not have a zero mean, then you will always say, oh okay, I'm going to work with a random variable x prime, which is the original xi minus the mu I. Okay, and whatever bound I get will be for that. So in that sense, it's totally fine. You can assume all your random variables are mean zero. Okay, so this is like shifting the origin. So assume all of them are mean zero. And if you know that each of those random variables is always bounded in magnitude, okay, so actually you don't need it like literally bounded all the time, you need it what is called almost surely, but forget this for a bit. Okay. So suppose you know it's always bounded, okay, then for any t, you have that the probability that it's more than t is something like, which is exponentially small in t. Okay. The difference between this and this is that here it was 1 by t squared, okay, while here it's something like e to the minus t squared. Okay. So that's the nice thing about about Chainoff Born or Bernstein's inequality. Okay, so it's way stronger than what standard, what typical Chebyshev's inequality type bounds tell. Okay. So yeah, so in your homework you'll have a very simple setting of just coin tosses, where you will analyze how, what Markov's inequality tells you. Actually, it tells you almost nothing. It tells you that the probability that you get n heads is something like less than equal to half or something if you have uniform coin toss. Okay, but you expect it to be really tight around n by 2, right? So Chebyshev's inequality tells you that, oh, it's n by 2 plus minus some 10 times square root n. But well, if you use Chernoff, then you get like really tight concentration. Okay, so that's that you will see. Okay, but this also essentially says the following. So it says that if you have a sum of independent random variables, okay, and each of them is not very big, okay, that's what is captured by this less than or equal to n. You need that condition because if one variable can be huge, then based on what happens with that variable, the sum could just be affected a lot. Okay, so you need something like that. So what it says is that the sum is only a few standard deviations away from the expectation. And so this messy expression essentially says that. So any questions on the message of these things? So you should remember that, essentially what it says is that it's around a few standard deviations away from the expectation. Yeah.
Should the standard deviation show up in the probability on the left-hand side? Like, should it be t times sigma?
Yeah, so that's a good point. So can anyone answer where it's showing up? It is showing up in this expression, but I'm just trying to see,
Because it's xj mean standard, the expectation of xj squared is the variance.
Yeah, exactly. Okay, so this is actually sigma squared. So the normalization of the t is a little bit different in my previous bound and this one. So here it's saying that, here I should be really setting t prime equals some t times sigma, and then you would get something similar to what I have. Or rather, I should be setting t equals t prime times sigma. Then use this result with t, and then I would be getting what I have. And there's this extra term that depends on the m, which usually is dominated by the sigma squared part. So usually what happens is that this part dominates this, and so essentially this is the one that remains, and that goes away. Okay.
What is that then?
M is a bound on each of these things. Okay. So yeah.
So that is E of xi square, right?
Is sum over j E of xj squared. Okay, and that's because these are independent variables, so the sum of the variances is the variance of the sum.
Xj is xi minus mu.
No, so all of these are independent variables, okay, and all of them are mean zero. Okay, so that's, yeah. Alright, so this is what this says, and it's it's a pretty powerful inequality. We started using this in this one application. Okay, so it's random walk on a line. We define this process like, suppose you have a particle that starts at the origin, and at every step either takes one step to the right, moves 1 unit to the right or 1 unit to the left, uniformly at random. Okay, and it has no memory. It always just walks around. Okay, and the question is, how far do we expect to be from the origin after t steps? And yeah.
About the previous slide.
Yeah.
Sorry.
1 second.
Yeah, I'm sorry. We go on. At the denominator of the expected function, we say that is sigma squared, but I wonder if we need also expected value of x of j squared to compute sigma squared.
To compute what? Sigma?
Sigma squared is expected value of x of j squared minus expected value of x con j.
Right. But in this case, each one is a zero mean random variable. So the expected value of xj is 0. So you're right. I mean, that's what you would ideally need. But each expectation is 0.
So what is that t equals to t prime sigma? Can you just explain?
So he asked this nice question that, okay, so the way I wrote this previous expression is like saying the probability that x minus mu is more than t times sigma is less than equal to 1 by t squared, right? So here I don't have this t times sigma, I just have just t here. I mean, that's because I got this from Wikipedia where they normalize differently, right? So yeah, so I always like to think of it as multiples of the standard deviation, because that's intuitively what's going on, right? So you know that your random variable at least deviates as much as the standard deviation, and all these bounds tell you that they don't deviate much more than that. So you've got to set t to be something times the standard deviation, and then you get the probability that's more than t prime sigma is less than roughly e to the minus t prime squared. And the earlier bound would have been something like 1 by t prime squared, and this one tells you it's e to the minus t prime squared. I mean, there's always the small constants and so forth, but for t prime, which is somewhat large, this bound turns out to be significantly better. Okay, so that's why people use Chernoff bonds as opposed to things like this. Because often t prime will be some function of the problem. It will be some log n or something like this, then you get extremely high concentration. So, yeah. Alright, so that's the, yeah, well, that's a good point. Okay, so now moving on to random walks on a line. So let's now, the reason I'm doing these bunch of examples is because I want you guys to get a sense of how to use these bounds. And yeah, and that's will come here hopefully. So what we are saying here is that now you have a process that's going on, okay? And how do we view this as a sum of random variables, right? So this is what, we started looking at this last time, right? So we said that, yeah, do you guys remember what we said? Suppose I call y, I don't know if I call it x or y, but let's call y sub t the position after t steps. So, can you write this as a sum of independent random variables? Remember, all the concentration bounds we know are for sum of independent random variables, right? So, yeah. So how would you write this as a sum?
Each time step we considered a random variable.
Sorry?
At each time step we considered a different random variable.
Yeah, so at every step we said that you define x sub I, okay, to be plus 1 if we moved right, and minus 1 if we move left. Then yt is equal to sum of over I going from 1 through small t of x sub I. And this is nice, this is now a sum of independent random variables, right? Because the process had no memory, it's independent random variables. So, and that's what this is. So now, yeah, so now it's a sum of independent random variables. And if you want to use this Chainoff bound, what you've got to compute is, you've got to have a bound on these guys, you have to know what the m is. And you've got to know what this sigma squared expected value of xj squared. Okay. So already it's in a good form, right? We know that the means are all 0. Okay, so the mean is 0. E of xi is 0. So what is the m in this argument? M is 1 because it's always plus 1 or minus 1. Right? So the magnitude is always at most 1. And now what is E of xi squared for any I? It's y.
It's -1 times -1 or 1
Yeah.
times 1.
So it's always -1. I mean, it's xi squared is always 1. Therefore, the expected value of xi squared is always 1. Okay, so xi squared is 1. So now what does So what does Chernoff Born tell us? So it tells us that, let's use this form of Chernoff Born. Okay, so then it tells us that probability that sum over I xi, that is y sub capital T, is more than, just to avoid confusing small t's, capital T's everywhere, let me write s here. Okay. Probability that this is more than s is less than or equal to e to the minus, actually I don't have space here, so let me write out here. Okay, so this is less than or equal to e to the minus s square divided by, so I need the sum of the xi square. Right? So what is that quantity? Yeah, it's 1 summed up t times, right? So it's capital T plus 1/3 of m is 1, so it's just small t, small s by 3.
So you need a half on the numerator?
Was there a half? Yes. So, right. So let me write this as 2 times this. Okay. I should just write fraction as a fraction to make clearer, but yeah. Okay, so, but hopefully this is clear to everybody. So you have s squared divided by 2 times t plus s over 3. So now, what should I set s so that this becomes pretty tiny? Like suppose I want this to become 1 over 100. So I want this to become 1 by 1000. Okay, so this is the probability of this being s, more than s. Right? So what should it be if I want this probability to be tiny? And we can solve for it, right? So we can always say I want s squared by 2 times t plus s by 3 to be roughly log of that, right? So log of negative log of 1 over 1000, let's call it 10. Okay, so it's significantly less than 10 probably, but let's call it 10. Okay, so then you have to solve for this, which essentially amounts to s being, you can verify this, the s being roughly some constant times square root of t. Okay, so it's like, maybe it's like 4 times square root. Okay, because the small s, as I told you, that s by 3 is always, usually is much smaller than the first term. Okay, because, and this you can verify. I mean, if you don't trust me, you can start by, on the right side, plug in 4 square root t in the first bound, then you'll realize that, oh, the numerator becomes some 16 times t, okay, and the denominator is 2 times t plus something small, right? Because square root t is usually much smaller than t. T is an integer and so on. So you get something like that, and you get at least e to the minus 10. Okay, so that's the problem. But the point here is not the constants. The point here is the fact that it's something like square root t, right? It's some constant times square root t. Okay? And square root t is the variance. So what this is saying is that the probability that it's more than 4 times the variance is less than 1 over 1000. Okay, so that's the message here. Okay, so the standard deviation sigma in this case is root t. So we are saying that you are actually, it's actually not much more than the standard deviation. Okay, so I'm going to just pause here for a bit because most of it is calculation, but I'll just pause here for a bit and read math question.
The 1 over 1000 is the probability that it's more than how
4.
many standard deviations?
4 times.
4
Yeah.
standard deviations? Okay.
Yeah. And and what you can see is that now if I replace the 4 by an 8, you get a probability that's extremely low. You get like e to the minus 40 or something like this, which is like super tiny. And that's the thing that Chernoff's bound gives you. That as you change this constant a little bit, your probability becomes extremely tiny. And yeah, so that's why it's very powerful. Like if you use Chebyshev, you would get something like this. You would get that the probability that it's 4 square root t is less than 1 over 16 or something like this. But now if you replaced that 4 with 8, you would get 1 over 64, which is better but not that much better. Okay, but if you use Chernoff, you would get like super tiny probability. So that's something to keep in mind. Okay, so another simple example. So biased random walk. Okay, so what is this? So here, suppose you have a particle, again starts at the origin. Now suppose that it has a bias towards moving to the right. Okay, what I mean by that is that with probability 2/3, we move right. Probability 1/3, move left. Okay, so how would you now think about this process? So again, the question is the same. The question is, where are we after t steps? Okay, and you can also think of this as saying, you want some confidence interval, right? So you want to say that, oh, I am in this range with good probability. You could see the previous thing, I was also saying the same thing. I am around the origin and I am in a 4 times square root t or 8 times square root t length interval with extremely high probability, with probability at least like 99.9%. So that's what you could think here. And now we want a similar claim out here. Right, so how would you analyze this?
Can be done the same way, but this time the mean won't be there. But still they will be independent random variables because it's a memoryless. Well, I mean, at each step it does not. I mean, the decision does not depend on the previous.
Yeah, so that's the key, right? So you still have independent random variables. Okay. Yeah. So now, what would the random variables be, and now what is your so how would you analyze this? So we can go about the same way, right? We can write y sub t to be the position at time t. Okay, and this is equal to sum over I going from 1 through small t of xt. Now xt is a random variable that is 1 with probability 2/3 minus 1 with probability 2/3. Sorry, 1. So how do we use this previous theory now? So what he said is that the mean is no longer 0, right? So now we know that expected value of xt is 1 by 3. So it's 2/3 times 1 minus 1/3 times, right? So that's why the mean is 1/3. Right. So now how would you handle this? Right? So how would you go to how would you use the previous theory? Yeah.
You could define xt prime to be xt minus 1/3, so that your mean would be 0 because of linearity.
Exactly. So what you can say is that xt prime is xt minus 1/3. Now the expected value of xt prime is because of linearity of expectation. Excellent. Yeah, it is just 0. And now you can use whatever you had with xt prime. Now we have one slight caveat. To use the result, you need the variance of xt prime. Okay, so we need expected value of xt prime squared, which we can compute now, right? So xt prime is just this.
The variance will be same, right? For this case.
Would it?
It depends on your.
Are you saying, I mean, previously it was 1, right? So in this case, we can, I mean, if we are not sure, we can just follow the definition, right? So it's the expected value of xt prime squared. What is xt prime? So it's xt minus 1/3. So with probability 2/3, xt prime is 2/3, like 1 minus 1/3, right? So it's like 2/3 times 1 minus 1/3 whole squared plus 1/3 times, yeah, minus 1, right? Minus 1 minus 1/3 is minus 4/3. Okay, and yeah, so you can evaluate this. Maybe somebody can do this faster than me. So what's this? So it's like 27 or something plus
24 or 27.
what's this? 16. Is it?
Or
16.
8 or
Sorry, 24 over 27. 8 by 9. Okay. Okay, so this is less than 1. Okay, so so you can bound this by 1 to be safe. So it's 8 by 9. You could have said beforehand that it's going to be less than 1, but never mind. Okay, so yeah, so that's the bound you can have, and now you can use the same argument, right? So you can say that, oh, what is the probability that sum of x primes? So you can say that probability that sum over I going from 1 to t of xi prime is more than s is less than or equal to e to the minus s square, or whatever, right? So you can say the same thing. But now, what does this translate in terms of the t's? I mean, in terms of just the xi's? We are interested in xi's, right? So we are interested in the actual process, not the xi primes. Now you just use this inequality, this equality, to conclude that, oh, this is like saying probability that y sub capital T minus capital T by 3 is more than s. Okay. So you get the same bond as before, but you get it for y sub T minus capital T by 3. And so if you think about it for a bit, you'll realize that this is exactly like saying we now are centered around T by 3 and we are in a roughly square root T sized interval. Okay, just as before. Okay, so it's the interval is a little bit better now because of this 8 by 9. Okay, the variance is slightly smaller, so the interval is slightly better, but you still have the same qualitative behavior, but centered around T by 3. And this, if you're clever, you could have seen it beforehand, because you could say that I can always think of this as a slightly modified random walk, where I always take one step to the right, where I always take 1/3 of a step to the right, and then I have some mean 0 thing. Okay? So you could have said that, in which case it's equivalent to this analysis. Okay? So yeah, let's not get there, but I just wanted to demonstrate one example that the mean is not 0. Okay, and if the mean is not 0, this is what you do. You center it, and then you apply standard Chernoff. Okay, so this is how you do it. Okay, so now another very simple application. So predicting elections, right? So we know this is a hard problem, but if you had uniform samples, it's actually pretty easy. Okay, so what am I saying? So suppose you have two people. Let's call them R and P. Okay, so you have red or blue, right? So and you want to see which one is higher. And you're just assuming a simple. You want to see which is larger. Okay? So which one just has more numbers. Okay? So which one has more number of people? So the question is, how many samples do you need from the population? Right? So clearly, if you had the entire population, then you can just count everything and so on. Okay. But now, you know that there could be a reasonable skew, right? So maybe suppose the skew is like 30% R and 70% B. Then, how many samples would you think are necessary? And how do you think this number of samples would vary if it was much more even? Right? So suppose I told you there is like 49% versus 51%. Intuitively, you feel that to distinguish between these things, you need many more samples. Hopefully all of you feel that intuitively, right? Because a small sample will not give you a very good estimate of what is. Right? Now how do you formalize this, and how would we basically use the previous methods to reason about this? So that's what we like to see.
Are the percentages saying like the population percentages like that?
Yeah. So this is a percentage of the population. If you knew that 30% are red, 70% are blue, then intuitively if you sample a bunch of them, you can see more blues in your sample than the reds. Right? And you would be able to reasonably conclude, it's still with a certain probability, but you will be able to reasonably conclude that, this is more likely to happen. So how would you formalize this? Like, so formally the question is how many uniformly random samples from the population we need to predict the winner. Right? And we want to understand that as a function of the difference between these or something. Okay, we'll see what we get, and then that will tell us how we can understand. But first, how do we go about capturing this?
So I'm not quite sure I understand the full question that we're asking, but in terms of using the previous discussion, it seems like this is just the same standard deviation with probability of 49 versus 51%, right?
So what do you mean by you didn't understand? So what is not clear about the question?
So what's confusing for me is just we're trying to determine the number of samples we need to predict, right?
Yes.
And so and it's probably because I'm still trying to think about the biased random walking. So biased random walking was telling us the probability of this within the standard deviation of about 4 or something, right?
Right.
So, yeah, I guess this.
So here it's a little bit different, right? So here it's actually closer to what we saw last class, if you guys want a hint. So, I mean, in some sense, we have two kinds of things, and you essentially want to predict. I mean, so one way to formally start thinking about this is you could say, oh, yeah, everything that's red I'm going to map to +1, everything that's blue I'm going to map to -1. Then it's like asking if the sum is positive or not. Okay, so or you could say 0 or 1, something like this, and then you want a threshold of half. Right? So, but let's stick to -1 and +1 and -1, okay, just for arbitrary sake. Okay, so then we want to know if the sum So let's assume there are lots of people, so probability that's exactly 0 is negative. So that's yeah. Okay, so now how do we formalize this? Now it's like you have an array you're sampling, right? So how do we formalize this? So if you are getting confused by the numbers, sometimes it's better to just fix the numbers with something arbitrary. Okay, so let's fix this case. Okay, so you are trying to determine something, and you're trying to determine if the sum is less than 0 or bigger than 0, and you're doing it with samples. Right? So you're asking, I have this population which I don't know. There are capital N people, let's say. So I have A1, A of 1, A of 2. Then each one is either +1 or -1. I essentially want to know if the sum is 0 or not, right? So that's very similar to what we tried to do last class. So what we are estimating the sum is like we are sampling a few people at random, and you are looking at this empirical sum. Right? So yeah, so how good an estimate is that? Yeah.
I think the thing that's hanging me up, I don't know if it's hanging anyone else, is I mean, you could make a prediction off of just one. It wouldn't be a very good prediction. I mean, it has to do with how many people you sample, right? So I guess that's
exactly.
what I'm confused about. I don't know about is the more people you sample, obviously, the more precise your numbers should converge on the population.
Right.
Right.
And we are trying to understand how that quantitatively, how that happens. Right, so I mean that's what we want to. I mean that's the goal. So that's what I mean by how many samples do we need to predict with a certain confidence. Right, so maybe that's part that was not clear.
That's the thing is the
confidence,
yeah.
Right, so we need to predict with confidence, let's say at least 99%. Yeah, sorry, yeah, I think that was what.
That's good, yeah.
Yeah. Okay. So suppose you want a confidence of 99%. How many samples do we need? And what I wanted to illustrate here is also this fact that if the split was 30-70, then you need fewer samples. If the split was 49-51, then you need more samples. Right. So that's the other part of what I wanted to highlight. So yeah.
I mean, the split of what?
The number of R's versus number of blues.
Before the election.
No. So there's no, I mean, see, this is all, imagine everybody has already made their decision, okay? So one way, after the election, you can go count the whole thing. But before the election, you're doing some kind of surveys and you want to ask a bunch of random people. And you obviously cannot ask everybody, and now you want to know that, okay, so suppose I want a confidence of 99%, then how many people should I sample? Okay. And as you were saying, I mean, somehow if your split is pretty even in this to begin with, then you expect a lot more people to ask if you want a confidence of 99%, right? I mean, in the limiting case, if like it was like almost exactly split, then you literally need to ask everybody to be sure that right? So that's what I want to illustrate. Yeah.
In the previous class, we did a concept like we were determining how many numbers we need to see if it is this much closer to the mean.
Mm-hmm.
So it's something like
Yeah. So I mean, it is very similar, right? Because morally, that's what you're doing. I mean, here we are not determining if it's close to the mean, you're determining if it's bigger than 0 or less than 0. Okay? And yeah, and that's part of the reason why it relates to the mean. But yeah, so
Could you use the bias in the underlying population to recenter from 0, right? And then calculate the probability that your deviation would not overlap 0 using Chernoff's method, right? And make sure that that probability is less than 1%.
exactly. Okay, so let's that's precisely the point, and we'll try to see how you execute that plan. Okay, so what he's saying is, so suppose I sampled a random thing here. Okay, so I don't know what this ratio is, but let's call it P versus 1 minus P. P versus 1 minus P. Okay, so it's some probability P, right? And yeah, so that's the fraction of R's. Let's call it P. Fraction of B is 1 minus P. Now, if I sample a random element, okay, and I call its value xi. So this I has nothing to do with A of I. Okay, so this is so this is the ith trial. Okay, so I sample some random element. Let's call it just x to be clear. So just x randomly from this array. What is the expected value of x? Remember, this is all we know, right? I mean, in some sense, what we are doing is we are sampling a bunch of random elements, and our test is uniformly at random. We are getting x1, x2 up to x some t, okay, and or k. Right? So this is what we used to call it k. We are testing if sum over I xi is bigger than or equal to 0. So that's the test of saying R has worked. Right, so this is our test. So we need to analyze how good this test is, essentially. Right? And I have another slide. Yeah, so I have another slide. So what is expected value of x in this case?
2p minus 1.
Okay, so this is p with probability, it's 1 with probability p and 1 minus p. So this will end up being 2 times p minus 1. Okay, so that's the expected value of p. And this is true for any I, right? So for any I, this is expected value of xi is 2p minus 1. What's the, yeah, I want to, part of it is I want to illustrate to you how mechanical this is. Okay, so in some sense, this is your random variable, right? Xi's are your random variables. And expected value of the xi's is 2p minus 1. What is expected value of xi squared? That's the variance for each xi. Right? So this also you can compute. So again, these are -1 and 1. So it's all right. So is this what matters, or yeah? Yeah, let me erase this. Okay, so remember, to apply Chernoff, you need mean zero randomness. Okay, so to follow what you're saying that, oh, I need to recenter this now. Okay, so I've got, and the bias of course is 2p minus 1. And intuitively, why does 2p minus 1 make sense? You guys see?
For half, you get 0.
Yeah, so if the split between R and B was exactly half, then you get 0. Okay, so, and if it was 30-70, then this is a bigger absolute number, right? In magnitude, this is a bigger number than if it was 49-51. Okay. So in that sense, 2p minus 1 makes sense. Okay, so the magnitude will be higher if it's more unbiased. Okay, so that's, yeah. So often it's good to, once you do the calculation, to make sense of the number so that you kind of get an intuitive feel of, oh, I'm on the right track. Okay, so that's, yeah, so the 2p minus 1 has that property. Okay. So now we can define xi prime to be xi minus 2p minus 1. Okay. And now we are interested in, yeah, so this is 1xi. Now if I use standard concentration bounds, what I'm going to get is that probability that sum over I xi prime is more than t is less than or equal to something, right? This is what I've used, yeah, I've not used t. So this is what Chainoff Born is going to tell me. And what does this translate to? This translates to sum over I xi minus p times 2p minus 1. Oh, sorry, I equals 1 through k, right? So minus k times 2p minus 1 is more than t. And that's like saying the empirical sum, this thing, and this is equivalent to saying sum over I going from 1 to t more than t plus t times 2p. Okay, so this is just I'm just trying to write down what this implies. I mean what my concentration bound will give me. Okay, at least the left side. Now let's look at the right side. Right. So now to evaluate the right side, you need the variance. So you need something like, you need what this expected value of xi prime is, square is. And what is that? It will be something messy, but I think it's important to know this. So let's try to understand this. Okay, so xi prime. So this is 2 times 1 minus p with probability p. And is that correct?
1 minus.
1 plus p, right? So, I mean, I might be making a mistake, so please make sure I'm not. Okay. So the first part is correct, right? So if xi is 1, then that would be 2 minus 2p, which is 2 times 1 minus p. If xi is minus 1, then it would be minus 1 minus this thing, which is, oh, it's just 2p then. Okay, so it's just minus 2p with probability 1 minus p. Right, so that's x minus p, x prime, xi prime. So its squared will be clean now, so its squared would have, so the 4 is common, and you have 4p times 1 minus p whole squared plus 1 minus p times p squared. Okay, and this is just 4p times. Okay, because p plus 1 minus p is 1. Okay, so you can verify this. So this will be 4p times. So this is this is actually the standard deviation. I mean the variance of any biased random variable. Okay, so probability. Okay, so anyway, so if you don't follow this calculation, it's not important. Okay, so just believe that the expected value of xi prime squared is that. So that's this. Now what this tells us is that this is exponentially small. This is e to the minus t squared divided by 4k p times 1 minus p plus whatever is so there's a t squared by 2 here, as somebody would just pointed out, and here you also have m, which is, what is m here? You can always just use 1, right? Every number is 1 or minus 1. So to be safe, let's use 2 so that nobody feels, so we just get t. Okay. So this is what we want. I mean, this is what actually Chainoff Born tells you. Okay, so this we know is true. All right. So now, why does this make sense? I mean, what should we set t to be for us to be sure, right? So what are we trying to do? So our test is going to be this. Right, so this is the probability that R wins. Right, so this is going to be our test. So we have two cases. I mean, P could be bigger than 1, P could be less than 1. Right? Sorry, P could be more than 1/2, P could be less than 1/2. Right? So P is, we don't know what P is, but it's one of the two cases. Okay, so let's stick to one of the cases. Okay, let's stick to, let's say, more than half. Okay, and try to understand what's going on here. So let's think of, think P is, so now what are we saying, right? So this is a number that is some constant times k now. Okay, so it is, because P is more than half. Okay, so it's some constant times k. And what Chainoff Born is telling us is that that for any small t, probability that this is more than t times that number is something that's exponentially small. Okay. So, but our test is actually sum of xi is more than 0. Right? So what should you set t to be? Okay, so again, let's go back. Okay, so this is actually somewhat simple. So we are, I think the algebra is getting confusing, right? So it's even confusing to me. So let's make things clear. Okay, so we have things being -1 with a certain probability and 1 with some probability p. Right? So, and we took a bunch of samples and we want to see if the empirical sum is positive or not. Okay. So, what we know is that if I took basically infinitely many samples, so if I took the whole thing into account, my empirical sum is going to be something like 2p minus 1. Right? The average is going to be 2p minus 1. Because, and I've assumed just for concreteness that p is more than half, so I drew it to the right. Okay. And that's what the expectation was telling us. And now what we want to ask is, what is the probability that you see something that is positive, right? So essentially we want to bound the probability that you are further from this average by something like 2p minus 1 times k. So that's like saying sum over I xi by k must deviate from its average, which is 2p minus 1, by a factor of, by at least 2p minus 1. And that's like saying, oh, I've got to set t to be k times 2p minus 1. Okay, minus of that, but it's the same thing. Okay. So I've got to set t so that the absolute value of t, so the deviation needs to be k times 2p minus 1. Okay, so the deviation from the expectation. So the deviation for the average is 2p minus 1, therefore the deviation for the sum itself is k times that. So that's what we have there. And now everything works out, right? So now what we need is, this quantity is what we have got to simplify. After you set t to be this. And now you can work this out, so you're going to get something like minus k times 2p minus 1. And if you want basically this thing to be small, you can verify. So the k will have to be large if 2p minus 1 is tiny. And that's kind of what we were getting at initially, right? 2p minus 1 was the bias in the election. So if the bias was large, then to have a good confidence, you need, you don't need that big a k. Okay? So think of 2p minus, if p was 0.7, then 2p minus 1 is something like 0.4. But if p was like 0.51, okay, then, let's see, if p is 0.7, then 2p minus 1 is roughly 0.4, is equal to 0.4. If p is 0.51, then 2p minus 1 is, it's 0.01 or something like that, right? So, maybe 2, right? So, but it's significantly smaller. Okay, and that's why this k squared times 2p minus 1 whole squared kind of is an important thing. Okay? And if you want this whole ratio to be large, you need k to be big. So, so this calculation, you will do the explicit calculation in the homework, but this is what this is. Okay, so, but morally, this is what you want to see, right? That if your bias is small, you need more samples to get a good confidence. Okay. And it's intuitively true, but this calculation tells you the exact numbers that you need. So I'm going to leave it at this. So this is, so it's a bit messy, so I don't want to get into too much detail. Okay. But this is more interesting. Okay, so this is hashing. This is another example. Yeah.
So I still didn't understand how this can be used to estimate the direction because we don't know P is. How do we,
Right.
if you want to estimate direction, in some sense P is what we are trying to find out.
Yeah. So no, so that's the thing. So it's a good point. So all you get is, if I take so many samples, then my confidence depends on the P. Okay. So this is a great point. So this method doesn't tell you anything. So it's more of an analysis method. So what it tells you is, if you had some knowledge of lower bound on P or something, then it tells you that so many samples are enough. Okay? But if you don't know P to start with, this doesn't, all it can tell you is, oh, this guy did 100 samples, that was not good enough. Okay? Because the P happened to be much very close to 1. Okay? So it's not telling you an algorithm. To have an algorithm, you have to do something called cross-validation, where you get two different things, make sure your sum was consistently more and stuff like this. Yeah, but this is it's a good point. So we are only trying to understand how many samples you need theoretically if I knew P. Okay? So yeah, actually this is good to clarify. Okay, so if I knew P, this is the number of samples. But this is not giving you an algorithm.
But if you knew P, you wouldn't be doing it anyway, so.
No, this is for the analysis sake, right? So what this is saying is, so sometimes about an election you could have knowledge that, oh, okay, it's not going to be that close. It's going to be at least 51-49. And then this is going to tell you that, 100 samples suffice to verify that claim. Okay? And so now you could ask, okay, what if I didn't know P? You could say, I do 100 samples, do it twice. If I get differing answers, then it means something was wrong, my estimate was off. Okay? And then you can do other stuff. Okay? Yeah. So that's called cross-validation. You do two different things and you try to get. Okay. All right. So actually we'll see something like this. I don't think we'll get to that today, but we'll see that next class. It's how you estimate sizes by, it's a similar idea. So, alright, so hashing / load balancing. So the reason I gave this example is because, so one of the places where randomized algorithms are used a lot is when you're dealing with uncertainty. Okay, so if you have, suppose you have a bunch of requests coming in, you want to assign them to, so imagine you have like 5 different booths. You have a bunch of people coming in, you want to assign them to booths. Now, you could say that, oh, I'm going to carefully keep track of how many people are there in each booth and I'm going to assign them. So this, if you don't have 5 booths, but if you're like Google and you have a search query and you have a million servers, it's impossible to ask to query every server and in some sense figure out what load it has and stuff like this, right? So you might just want to do something online. These are what are called online algorithms, where you just figure out, do randomly or something like this, right? So randomized allocation kind of works pretty well. Okay, so I don't know if I put this up, but yeah. So one way of doing things is to say, okay, I'm just going to distribute things randomly, okay, and hope for the best. Hope that the load is uniformly distributed. And intuitively, you would expect it to be uniformly distributed, right? Because I'm giving uniformly at random. Now, we want to understand if it's really like that. So, formally, what we want to say is that if you have n objects and you hash them into an array of size c times n. Okay? So, this is a little bit different than the example I said. So, I have n objects, and c could be bigger than n, could be smaller than n. Okay, so think of it as some small constant. Okay, so think of it as 0.5 or something like this. If you want, you can think of a constant bigger than 2, bigger than 1. Nothing really changes. Okay, so you will see. So let's call this m. Okay, so you have m buckets. Okay, so so these are all the buckets. And each one goes uniformly at random to one of these things. Okay, so the question we want to understand is how balanced are these buckets? So the first thing you can ask is, what is the expected bucket size? Intuitively. Sorry? You expect n things to be in one bucket? No. Yeah, it's n by m, which is 1 by c, I think, right? Yeah, so it's expected bucket size is n by m. Okay, so how do you formally write this? And this is the bucket size for any bucket, right? Because of symmetry, you expect everything to be the same. So how do you formally write this? So this is one example where if you try to compute the expectation based on its definition, it turns out to be very messy. Because suppose I fix a bucket and I say what's the probability that the bucket size is 1? Okay. Then you've got to say, oh, what's the likelihood that exactly one person matches to that and everybody else does not match to that. And then you can do this calculation, it turns out to be what it is. But if you guys want to, indulge yourself, you can do this calculation, right? So it is, you could say, okay, what's the probability that the load is k, right? So let's fix this bucket and let's call y, this is bucket I, let's call yi the number of objects that get hashed to yi. Could say what is the probability that yi equals k. And this will turn out to be something like n choose k times 1 by m to the k times 1 minus 1 over m to the n minus k. Okay, so not as messy, but still not the best thing to work with, right? So it's looks messy. Okay. So, and now all you've got to do is just do sum over k of k times this probability of yi equals k. And you use all your manipulative skills, you can get that this is exactly equal to n by m. Okay. So one could do this, but this is where it turns out you can do some very cute linearity of expectation argument. Okay. So this is what I was saying last time when I was saying that somehow linearity of expectation can help you out in kind of unexpected situations. Okay. So writing a complicated variable as a sum can often help simplify computations. Okay. So given that hint, how would you go about writing yi as a sum of random variables? Okay, so yi is the number of things that got hashed to bucket I. Yeah?
Just make it a Bernoulli 0, 1, whether it goes in that bucket or doesn't.
Yeah, so you could say, okay, I look at every object, okay, so it's 1 through n, and I have a variable which I call x, let's call it r sub I, which is a Bernoulli. Okay, so this is a random variable. Okay, and this is 0 if object I, it's 1 if object I goes to bucket, object R goes to bucket I. Okay. Remember, we are focusing on bucket I. Okay. So we want to know if object R goes to bucket I and 0 otherwise. So in this language, yi is just x1i plus x2i plus so on plus x capital N I. So this is just the sum of who all goes into this. Now I can say, okay, expected value of ei is sum of the expectations. Now what is expected value of xri? So it's, it's just the probability that it's 1, right? It's a 0, 1 random variable, it's a Bernoulli as he's saying, so it's just the probability that it's equal to 1. And what is the probability that xri is 1?
1 over the number of buckets.
Yeah, 1 over the number of buckets, so this is 1 by m, right? So now by linearity of expectation, you basically get n by m. Okay? And that's it, it's just no algebra needed this time, except summation. So this is where it often helps to write things. And once I've written this, right, so now I can say, oh, I can use all kinds of concentration bounds. I could try to answer things like, oh, what's the probability that the bucket size is more than T? Okay, so this is what we'll see next time. So just to, yeah, and you can also argue what is the max bucket size. So, alright, this is where I was supposed to have done that.